In glycolysis, our inputs are going to be glucose to NAD+, so we need something to accept hydrogen ions and carry it temporarily. To ATP are actually going to go into this process because we actually have to power some enzymes to make things happen. And we also need the substrate of two ADP and two inorganic phosphate groups in order to synthesize them into further ATP. You can't make ADP without or ATP. You can't make ATP without ADP and inorganic phosphate. Now we are going to put 2 ATP into this process. We're going to get 4 ATP out of this process, but that means we net positive 2 ATP. Our end products, again, are going to be 2-pyruvate, 2 energy intermediates, NADH, and 4 ATP with a net of 2 ATP, as I already said. This is taking place in the cytosol. Yeah, we don't need our specialized organelles for this. This is why it's so important for anaerobic cellular respiration. This does not require oxygen. It does not require organelles. So even if something's wrong with your mitochondria, you can still do this. If there's no oxygen, you can still have glycolysis. You can eke out a tiny amount of ATP, even without mitochondria. Now here is our very, very detailed step-by-step glycolysis. There's a lot going on here, but we're going to focus on a couple of details. I'm not really interested in you learning every single name of every single step here. What we're going to be interested in here is going to be a few different concepts. So first of all, we're going to talk about isomers, which isomers are a chemistry concept. An isomer is 2 different molecules with the exact same chemical makeup, the same atoms. But those atoms are in slightly different positions. They're bound to different things. So we're going to have some isomerization reactions, which means the atoms are the same, but our enzyme moved an atom from here to here. That's what an isomerization reaction is. It sounds really fancy, but it's pretty straightforward. Like if this is going to work, you can't be over there, you need to be over there. You've got an isomer. And then we will discuss the role of an enzyme that impacts glycolysis, and specifically some of these enzymes are going to create isomers. So like I just said, there is an isomer that just moved it from here to here. We are going to name some of those enzymes that take part in this reaction, and some of those enzymes are going to create isomers. So let's go into here. So we start with our glucose. And the first thing that we need is for our enzyme hexokinase to add a little phosphate group to it. We're going to, let's see if there's anything else that happened. We took that carbon, no, carbon's still there. OH, we took some of those hydrogens away. We put a little phosphate group right there. So this is glucose 6-phosphate. We added a little phosphate right there. And that's what hexokinase did. And it required ATP in order to do that. Now we've got a phosphate group hanging out on this glucose. Now we're going to isomerize it. We're going to turn it into something with the same chemical formula, but a different shape and way things are bound together. And now it's a fructose. It's a pentagram instead of a hexagon. A pentagon rather than a hexagon. Pentagram. It was just Halloween, so that's fair. So it's a fructose instead of a glucose now. But that was an isomerization reaction. And now another enzyme is going to be phosphofructokinase. So it's acting on this fructose here. And it's actually adding another phosphate group on here. And now we've got fructose 1,6-biphosphate. So there's 2 phosphate groups, hence the pi there. I don't want you to memorize these names, but maybe we do need to know that hexokinase and phosphofructokinase are 2 of the enzymes acting on this system, and give some sense of kind of what they're doing there. So the main difference between this and this is the shape of it, but the actual atoms, if you count them out, should be the same. So that's an isomer. Now we've got 2 phosphate groups. This next bit, it stops here, it starts back up here. So this could have been like one long image. This arrow goes to this arrow goes to this. Because there's a phosphate on either side, but slightly different chemical makeup on either side, a slightly different balance, we end up with two very similar but slightly different molecules. There's a phosphate here and a phosphate here. We've got a 3-carbon backbone, 3-carbon backbone. So we've got dihydroxyacetone phosphate over here, and then we've got glyceraldehyde 3-phosphate over here. And they are both going to undergo some similar reactions the rest of the way down. At this point, we can introduce our energy intermediates. And what you're going to see is we're going to be taking hydrogens from either one of these, and we're going to put that hydrogen atom onto one of our energy intermediates. So our input here is 2 NAD plus and 2 inorganic phosphates. And we're going to get out of that 2 NADH and 2 hydrogen ions. But we've got even more phosphates on this molecule now, and we're gonna, again, it's just transporting these things to where they need to go. We need this phosphate on the molecule right now, and later we're gonna use that phosphate to make our ATP. So we've got 2 phosphates. Now we introduce two ADP, and we are going to do a synthesis, an anabolic reaction that turns that into two ATP molecules instead. So on and so forth. And so that's the idea, is we gave them the phosphate groups temporarily to bring that phosphate group over to the ADP. We gave something a hydrogen in order to bring that hydrogen over to somewhere else and utilize its energy elsewhere. And I think I'm pretty happy with that. Again, you're not memorizing these names. I don't see any good reason to memorize those names. I want you to understand, we donated an inorganic phosphate. We donated hydrogen ions. We took hydrogen ions. We took inorganic phosphates. Enzymes help do this. Sometimes enzymes require energy. The goal is to get more energy out than you put in. Matter's not created nor destroyed, so the things that we put in, there have to be more of them. If we're going to get more energy out, we have to put more things in. Is that working for you? I hope that's working for you. So as I said, we put 2 ATP in, we got 4 ATP out, but we netted 2. So we got more energy out because we put more things in. Our end product back here was pyruvic acid, which is a 3-carbon backbone still. And there are 2 of them, remember? So we split this molecule into 2 different molecules here. We only followed one chain, but at the end of it, just assume this chain happened twice for each of those molecules. So you get pyruvate. But it's not pyruvate that goes into the Krebs cycle. Something else goes into the Krebs cycle. So we also have a transition reaction. Transition from the cytosol into the mitochondria means that we're going to take pyruvate and turn it into acetyl-CoA. This is going to release 2 carbon dioxide. So we'll go ahead and start from 2-pyruvate. That was the end of glycolysis. We are also going to need the substrate of 2-coenzyme A. We're going to, do I have a better one that actually shows the carbon dioxide being left from this? I need a better transition reaction slide. Give me a second to grab that. Okay, I like this a lot better. So what you're seeing here is your pyruvic acid has this 3-carbon backbone. And in order to transform that into an acetyl-CoA, we've got 2-carbon backbone and the coenzyme A here. We did actually lose a carbon and an oxygen from that molecule, or carbon and 2 oxygens from that molecule. So this is a process known as decarboxylation. This is a carboxyl group. And we lost it, so we decarboxylized it. So our transition reaction, therefore, is a decarboxylation reaction. Now, there's also something known as a carboxylation reaction. Anytime we add on a carboxyl group, then we've had a carboxylation reaction. So if this were going in the opposite direction and we had a 2-carbon backbone, we ended up with the 3-carbon backbone and oxygen was also part of the reaction, then we would have called that a carboxylation reaction. Okay. Now again, this is us transitioning into our mitochondrion. Here is our pyruvic acid. Here we are using an NAD+ to get an energy intermediate, NADH, as well as a hydrogen ion. And here we have carbon dioxide being released as a byproduct of this process. My jaw's getting sore from talking. That's what I'm doing. Okay. Now that was carboxylation. Remember, we just did carboxylation. Gaining a carbon dioxide is carboxylation. Losing a carbon dioxide is decarboxylation. Similar terminology here. Phosphorylation is gaining a phosphate group, and dephosphorylation would be losing a phosphate group. So the formation of ATP, by definition, is a form of phosphorylation. It's going to be a synthesis. We're going to take adenosine diphosphate. We are going to bond an inorganic phosphate group to it. We are putting energy into the bonds between those two phosphate groups, and that means that we have a high energy molecule at the end. Our inputs into the Krebs cycle. You know what? This was the glycolysis video. We just finished glycolysis and transition reactions, and that means it's time for our next video for Krebs cycle.